In this video, we're going to look at lesson 8.3, which deals with infinite series. Primarily, we're looking at infinite geometric series. And the definition of that is it's a sum of an infinite geometric sequence. So before, and I'll do a very basic sequence, I will start with 1. And so when we learned what a series was, if I'm multiplying by 2, a series, instead of listing them with commas, we are trying to find the sum of all those numbers. And we used to stop at a specific term position. But what this lesson is saying is we are not stopping for this. We are going on and on and on. And so in other words, we are going to infinity and beyond on this. We are going to keep this series going and going and going. Sorry, I couldn't resist. So we are going to go to infinity for it. So we're going to list them all off and go find the sum. Now in this case, there are two types of infinite geometric series. There is a divergent series and there is a convergent series. And it's actually what those words mean. If you diverge, it spreads far, far, far away. And so a divergent series is a series whose sum does not approach a value. The common ratio, the absolute value of it, is going to be greater than or equal to 1. And so I have here a series that starts at 1/16, and then I'm multiplying by 2 each time. So then I go to 1/8. So 1/16, 1/8. Then I have 1/4, then I have 1/2, then I have 1, 2, and you can notice in this case your terms are always getting larger and larger and larger. They are always increasing. So what does that mean? That means you are adding larger and larger numbers each time. Well, if I keep adding larger numbers and larger numbers and larger numbers every single time, then the sum, it would approach infinity because the numbers are getting bigger and bigger and bigger and bigger each time. But we don't say the sum is equal to infinity. We say no sum. And so when you have a divergent series, it is not possible to find the sum. The divergent series occurs when your common ratio has an absolute value that is greater than or equal to 1. So the example here, your ratio is 2. Even if I had a ratio of -2, the absolute value -2 is greater than or equal to 1, and that would be a divergent series as well. A convergent series is going to converge at a specific value. And so it is possible to find the sum of those. In that case, your ratio is going to be, the absolute value of it's going to be less than 1 for it. And the formula is this right here, A1 divided by the quantity 1 minus R. And so I have this example. In this case, I'm starting with a first term at 5. So I can plot the first term at 5, boom. I'm multiplying by 1/2, so 2.5. And I just keep going, 1.25, boom. And in this case, the terms are always decreasing. You, in this case, are adding smaller and smaller numbers each time. So in this case, we have the sum would approach a value. Because the numbers, as you keep this series going on forever, you're adding a very, very small number. It's not having a large impact at all. So you have divergent series and you have convergent series. So when we're going through this, the first thing we want to do is we want to find out, is it possible to even find the sum of the series? So we need to figure out first, is it convergent or is it divergent? And if it is convergent, if we can't find the sum of the infinite series, then we do it. So if we look at these examples right here, we have this infinite geometric series. We're told it's a geometric series, which means I probably, based off of this, I probably want to find R first, because the value of R tells me whether it's divergent or convergent. So if I want to find my common ratio of it, what we can do is we can take the second term and we can divide by the first term. Because when you're going from left to right, you're multiplying. So right to left, you're dividing. So I can take A2 and divide by A1 for it. And so when I do that, I'm going to have 36, and I'm going to divide by 54. Always simplify a fraction. So in that case, 18 goes into 36 2 times, goes into 54 3 times. My common ratio is 2/3. So right off the bat, based off of that common ratio, since that ratio, the absolute value of that ratio is less than 1, this is a convergent series. It is possible for us to find the sum. So I'm going to have the sum. The formula for a convergent series was A1 over 1 minus R. So I have my first term, which is 54. I am dividing by the quantity 1 minus my ratio, so 1 minus 2/3. So in this case, I have 54 over 1/3. Well, I'm dividing by a fraction, so I'm going to leave that 54 there, and I'm going to flip the 1/3 and multiply. So 54 times 3, the sum of this infinite geometric series is going to be 162. That's how you find the sum of a convergent infinite geometric series. Find the common ratio, determine if it's convergent or divergent. Convergent, go to town, use the formula, find it. Well, what happens if we have one that's divergent? So if I look at number 2, same idea. We're told it's infinite geometric, so I'm going to pay attention to that, and I'm going to take my second term, I'm going to divide by my first term. And that's going to give me my common ratio. So I'm going to take 3 and divide by 2. My A2 divide by A1. Now, I'm going to pause because I can do it right here. It doesn't always have to be A2 and divide by A1. If you feel more comfortable doing this and dividing these or vice versa, it's always just the next term divided by the previous term. Really the main idea behind how to find the common ratio on it. It's the idea of going backwards. So in this case, I'm taking 3 and dividing by 2. What we have here, our R value, since the absolute value of that R is greater than or equal to 1, this is a divergent infinite geometric series, which means there is no sum. The numbers are going to get bigger and bigger and bigger and bigger each time. So therefore, we're going to keep adding larger and larger and larger numbers. It's going to approach infinity. It's not possible. So let's look at number 3. Now, it gets more complicated when you're dealing with the fractions, but it's always the same idea. I'm going to take my second term, and I'm going to divide by my first term. I'm going to go backwards to find what is my common ratio. So I'm going to take 6 over 15, and I'm going to divide by 2/3. Now, when you divide by fraction, remember you flip and multiply. So that's 6 over 15 times 3 over 2. Now here, let's see, 3 goes into 3 once, it goes into 15 5 times, 2 goes into 2 once, 2 goes into 6 3 times. So my common ratio is 3/5. Again, I'm going to take a minute and just kind of talk about something. When you go through this, I mean, I use the common ratio formula. I took the second term divided by the first term, boom, got it. However, I'm told it's a geometric series. And remember, when you are multiplying fractions, you multiply the top and then you multiply the bottom. So in other words, think about it. What do I multiply 2 by to get 6? Well, I multiply by 3. And notice that's consistent on the top. You're multiplying by 3. Well, when I multiply 3 by to get 15, you multiply by 5. And notice that's consistent on the bottom. I'm multiplying by 5. And notice that's my common ratio. Even though they're fractions for the infinite geometric series, doesn't mean it's more complicated. You just have to remember, how do I multiply fractions? I could get my common ratio just by looking at the top and the bottom and seeing what am I multiplying by. Or if you want to be consistent, you can use the setup here. It doesn't matter which one you do, but just because it's a fraction, don't freak out over it. It actually makes it visually easier to see what the common ratio is. In this case, since 3/5, the absolute value of that number is less than 1. This is a convergent series. We have the ability to find the sum. We can take a1 and divide by the quantity 1 minus r. So I can take 2/3 and I can divide by 1 minus 3/5. And so in that case, I am going to have 2/3 over, let's see, 1 minus 3/5 is 2/5. So I'm dividing by fractions, so 2/3, I flip and multiply, so over 5 halves. And if I multiply these, let's see, the 2's can cancel, and I'm going to have a sum of 5/3. There we are. Find the common ratio, divergent versus convergent. Convergent, go to town, find the sum. Divergent, no sum. So let's look at number 4. Have this, I'm going to take the second term, I'm going to divide by the first term on it. So I'm going to take 9 over 6. Simplify that, that's 3 halves. If I take a look at that, well, since the absolute value of 3 halves of that r is greater than or equal to 1, this is a divergent infinite geometric series, which means there is no sum. Well, that was easy. 5 and 6, though, there's something that's unique about these two. Look at the series. You have a positive term, then you have a negative term, then you have a positive term. Looks like we're going to have a negative term. It looks like this pattern is going to repeat for both 5 and 6. Well, how does that happen? How do you rotate between a positive number and a negative number when you're multiplying? In that case, I can kind of look at it and think, well, maybe my common ratio is going to be negative, because multiply by negative is going to rotate between a positive number, negative number, and so on. So let's see, I'm going to take my second term and divide by my first term. So I'm going to take negative 8/9 divide by 8 over 27. Oh, it's fraction. Divide by fraction. Negative 8 over 9. Flip and multiply. 27 over 8. Let's see, 8 goes into 8 once. These two will cancel. I still have that negative sign. See, 9 goes into 9 once. 9 goes into 27 3 times. And so I'm left with a common ratio of -3. In this case, let's see, the absolute value of that common ratio of -3 is +3, which means it's greater than or equal to 1. So this is divergent, which means you have no sum. That was quick. You have to get comfortable with fractions on it, get used to it. Hopefully these problems are going to make it a little bit easier when you go through them. And the second term, I see this negative on it. So I'm going to take that -12 and I'm going to divide by the 16. So my common ratio is -12 over 16. That, of course, can be simplified into -3/4. First, determine whether it's convergent or divergent. Well, since the absolute value of -3/4 is less than 1, This is a convergent series. I have the ability to find the sum using my formula, A1 over 1 minus R. So I have 16 over 1 minus a negative 3/4. So I'm going to have 1 plus 3/4. So that's going to give me 16 over 7/4. Looks like I am dividing by a fraction again, so I'm going to keep that 16, and I'm going to flip and multiply. So I'm going to multiply by 4/7, which is going to give me a sum of 64/7. There is the answer. That is infinite geometric series on it. It's the first part of this lesson. Divergent versus convergence based off your common ratio. If it exists, if the infinite geometric series is convergent, use your formula. You have to get comfortable with the idea of fractions. You are expected to find the exact sum. Even if you go through and go, oh, it's a fraction, I'm going to write down the decimal. No, we want the exact sum. So you have to get comfortable with these fractions. Now, what part two does is part two is fun. I love this stuff. Is when you are writing repeating decimals, you can use infinite geometric series on it. So if I want to write 0.63 repeating as a fraction on it, I can break down 0.63 repeating. And if I just logically, 0.63 repeating is 0.63, 63, 63, dot, dot, dot. I mean, that's just going to keep going and going. Notice you're repeating the same number. But what's happening is, if I look at this 0.63, let me just put it right here. And I'm going to put this 0.63, I'm going to put the next one right here. But notice I'm going to put two placeholders, two zero placeholders that overlap where this number was. And if I were to add those two numbers together, those two positions together, I would get 0.6363. And so I'm going to keep following that. I can do this. I can take this 63, but notice this one right here has four numbers to the left of it. So I'm going to insert 4 zeros to the left of it so I don't overlap those, and then I'm going to put my 68. I can keep going on this. And so we're going to kind of write out the first three numbers on it, and we can change these into fractions each term. 0.63, if we think about our decimals, we have tenths, hundredths, thousandths, 10,000ths, dot, dot, dot. So in this case, 0.63 is 63 over 100. 0.0063, notice there are four spots here, and I have 4 zeros on it. And so that tells me I'm going to have 63 over 10,000. Keep the color coding. And let's see this one. I have 5 spots here. Sorry, 6. Let's see, I have 6 spots here on it, not including in front of the decimal, after the decimal, 6 spots. So I have 6 zeros down here. I have 1 million. So I have 63 over 1 million. So that's how you write it as the fractions for it. And then what we're going to do is we're just going to follow the same formula we've been doing. I need A1. If I think about my formula, the sum of an infinite geometric series is A1 over 1 minus R on it. So I need A1, I need R. And here's where that nice little trick comes into play is A1's given you, it's the first one you found out, that's awesome, that's easy, that's done. Well, how do I find R? Well, you could take A2 and divide by A1 like we've been doing, or I recommend this, use the shortcut. What do you multiply 63 by to get 63? And you're multiplying by 1. Boom, 1 on top. What do I multiply 100 by to get 10,000? Well, I have 2 zeros. I want 4 zeros, so I need to multiply by 100 on the bottom. Boom, there's your 100. So your common ratio really is a visual thing on this one. on it is, what are you really multiplying by to increase the number of zeros in the bottom? That's why we like to use the 100, the 10,000, the 1 million, or any number with 1 and zeros in the bottom for this. It's going to make that common ratio a little bit easier. So I plug everything in, and that's what this last step is doing. I have 63 over 100. Boom. I have my common ratio, 1 minus 1 over 100. So that would be 63 over 100 over 99 over 100. And in this case, I'll show it down here. What I did was I flipped and multiplied. So 100 on top, 99 on bottom. Look at that, those 100s. We're going to cancel out. And then, as always, because this is math class, simplify your fractions. 63 over 99 is 7/11ths. This is just a guided example to go through. We're still going to do a couple of the problems together on it. So my first thing when I'm doing this infinite geometric series is I want to write out the list of it. And I should probably read the directions on it. Is there are some things that we're trying to do every single time. We're trying to write out the number as a series. We're going to write out the fractions. We're going to then identify A1 and the common ratio, and then we're going to find the sum for it. So the first part, and we'll do this one in a little darker green. Write out the number as a sum of a series. So 0.21 repeating. So let's try it. We have equals. That was easy. We have a 0.21. I guess I'll use the dark green. So we have 0.21 plus. But what's the next term going to be? Well, the next term is going to be zeros where those first two numbers were, and then a 21 again. And then the next term is going to be zeros where these four numbers are. So I'm going to have 4 zeros, 1, 2, 3, 4. And then I'm going to insert what's repeating. I'm going to insert the 21. And if it helps, maybe I'm just going to do this. I have 0.21, 21, 21. And what I did was I took the first two numbers and I wrote them down. This number, this 21 is right here. However, I have 4 total spots. I have 2 numbers to the left of it. So I insert these 2 zeros to the left of it. But then this last one, this 21, if I'm looking at it, this one, I'll go purple. This one right here is right here. But I have 4 numbers to the left of it. So I insert 4 zeros to the left of it. So that's where those zero placeholders are coming from. That's mainly the big key, because after that, it's really the idea of counting the numbers on it. So there is the first part. And then I'm being asked on this, after I write out the series, and I'm going to put for it plus, because as we do go to infinity and beyond for it, we're going to put the plus ... on it. So now, let's see what the next part says. It says that we need to write each term as a fraction for it. So I will use blue for this one. So write each term as a fraction. So let's start it off. See, we have a 21 over, well, how many places do I have? I have 2 places, so I'm going to have 2 zeros. Plus, let's see, I have a 21 over, well, how many places do I have? I have 4 places, so I'm going to have 4 zeros, tenths, hundredths, thousandths, 10,000ths. I have a 21, and in this case, it looks like I have 6 numbers, so I'm going to have 6 zeros, 1, 2, 3, 4, 5, 6, 1 millions. And then, well, plus ... So there we go, we wrote them as fractions. Notice the top is always going to be the same number, because that's the one that's repeating. The next part, we are asked to find A1 and the common ratio. Let's do purple for that one. A1, well, that's simple for us right here. A1 is given to us as 21 over 100. We found that right away. And my common ratio, I'm going to use the trick. I'm not going to do A2 divided by A1 because there's just so many zeros. Is notice the top stays the same. So we are multiplying by a 1 on the top. On the bottom, notice we have 2 zeros, and we increase to 4 zeros. So I'm really multiplying by 100 on the bottom. There's your A1, and there is your R. The last part, and we'll do a lighter green for that, is find the sum using the formula for it. So my sum is A1 over 1 minus R. So I have 21 over 100 over 1 minus 1 over 100. And if I look at that, that's going to give me, I'll keep the 21 over 100. But 1 minus 1 over 100 is 99 over 100. There we are again, dividing by fractions. So I keep the numerator, I flip and multiply. See, I have a 100 on top and I have a 100 on bottom. So really I have 21 over 99, but do not be that student who does not simplify fractions. Always simplify them. And so in this case, 3 goes into 21 7 times, 3 goes into 99 33 times, and so the fraction is 7 over 23. Well, how do I know if I am right? Well, let's look at the calculator. 7 divided by 33. 0.212121. Brilliant, we have the right answer. So you can even check your answer at the very end for it. So number 8, same idea. And I'll try to remember to follow the same color coding for it, is first write out the infinite geometric series based off the repeating decimal. So this is equal to 0.325. Well, we'll write it out fully on it. So I have 0.325, and it's going to be after that 325, and then after that it's going to be 325, and then it's going to be dot dot dot. So the first one, boom, 0.325, done. Plus, well, I'm going to have to write down this 325. However, there are 3 numbers to the left of it. So I'm going to insert 0.1, 2, 3. I'm going to insert 3 zeros and then the 325. And let's look at the last one. If I have here this, you have this 325. So I know I'm going to add that. However, there are 1, 2, 3, 4, 5. There are 6 numbers to the left of it. So I'm going to have 1, 2, 3, 4, 5, 6 zeros, then the 325. And then the plus dot dot dot. And so notice I'm using these zeros as overlapping placeholders to not get the number we already put down on it. And so I'm going to then, see, after that we wrote them as fractions for it. So I'm going to use the blue. I have 325, it looks like, over, how do I write that as a fraction? Well, there are 3 spots. So you have tenths, hundredths, thousandths, 3 zeros. Plus, we know it's going to be a 325 over, well, the question is, what's going to go on the bottom? Well, how many numbers do we have? We have 1, 2, 3, 4, 5. We have 6. So 1, 2, 3, 4, 5, 6 zeros. Plus, well, we know it's going to be 325. 325 on top over the 3, 4, 5, 6, 7, 8. We have 9 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Boom, boom, boom. Plus, looks like dot, dot, dot. So we are using a lot of this idea of placeholders of tenths, hundredths, thousandths on them with decimals. Just to insert those zeros there. And we're just counting them to get the denominator. How many numbers are there after the decimal? And that's how many zeros we input. So we have next, I believe it was purple. Yep, A1 is 325 over 1,000 given to us. And then we got to find R. on it. R equals, well, notice you're keeping the same number on top, so you're multiplying by 1 on top. That's not bad. But what about the bottom? I mean, I don't want to do 82 divided by 1. So let's see. We have 3 zeros on the bottom, and then it goes to 6 zeros. So I'm multiplying by 1,000 on the bottom for it. There's a lot of counting with placeholders here, with these zeros here. And so that gives me my A1 and my R, and I can use green, my formula, and I have my sum equals A1 over 1 minus R. So I have 325 over 1,000 equals 1 minus 1 over 1,000. Let's see, the top's going to stay the same, 325 over 1,000, and the bottom is going to become 999 over 1,000. Dividing by fractions, so you keep the numerator, boom, 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 flip the denominator, so 1,000 over 999, and multiply. I have a 1,000 on the bottom and a 1,000 on top, and those cancel, and I get a sum of 325 over 999, which cannot be simplified, so it's going to stay as is. How do I know I'm right? Again, I could take 325 divided by 999. Boom, I see that it repeats. We have the right answer. Now 9 and 10 are a little more interesting on it because look at where the bar is. Don't be tricked on 9 and 10. When we're looking at it, I want you to see that the 4 right here, this 4 is not repeating. It is going to stay there every single time. And when we're writing this out, this equals this 0.4 on it. That is going to stay. That is not the repeating part. The repeating part is the 1, 2, 1, 2, 1, 2, 1, 2 after the 4. So when I'm writing the next term, I'm going to have to insert, just like we've done before, if I were to write out what this number is, it's 0.412, 1, 2, 1, 2, dot, 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 dot. Well, we took care of this 0.4, it's staying, it's constant. Well, I then got to take care of this 1, 2 afterwards. I have to insert a 0. There's one number to the left of it, so I have to insert a 0 and then my 1, 2. I then have to take care of this one. So I have that 12. However, there are, let's see, 1, 2, there are 3 numbers to the left of it. So I'm going to have to insert 1, 2, 3, then my 1, 2. Then I got to take out this one. So I have this 1, 2 I got to write down. However, there are 1, 2, 3, 4. There are 5 numbers to the left of it. So I have to insert 1, 2, 3, 4, 5 numbers left of it, then the 1, 2. And then don't forget the dot, dot, dot. That 0.4 is just going to stay there. It's not repeating. The only part that's repeating is that 1, 2 afterwards. So there's a little trick on there. Don't just go for repeating the entire time. Read the problem on it. So I'm going to take this 0.4 and I'm going to write it. And because that's the next part is I'm going to write it as 4 estimates. And I'm not going to simplify it. And there's a reason why. I'm going to keep this one here. That's the first part. The next part follows exactly what we've been doing on it. I have the 12, the 1, 2 repeating. So I'm going to put a 12 on top. Well, how many zeros are there? Well, not zeros, sorry. How many positions are there in the number? There are 3 numbers afterwards on it. So I'm going to insert 3 zeros on the bottom. Plus, I have my 12. Well, how many numbers after the 0? There's 1, 2, 3, there's 5. So I'm going to insert 5 zeros on the bottom. So I have 100,000. Plus, I have my 12. Well, how many total numbers after the 0? Let's see, 2, 4, 6, I believe 7 numbers after the 0. So 7 zeros on the bottom. 1, 2, 3, 4, 5, 6, 7. Boom, boom. And so that, don't forget the plus, dot, dot, dot. There we go. That is it written out as a fraction. The only part we're going to use our formula for is this part right here, because that's the infinite geometric series. That 4/10, and that's just going to be carried down on it. It's constant. It's staying 4/10. It's not adjusting at all on it. So in this case, A1 is 12 over 1,000. And my common ratio, let's see, it's going to be 1 on top. Hopefully you figured that one out because you're not changing the top. On the bottom, I have 3 zeros, and then I go to 5. So I want to insert 2 zeros. I'm multiplying by 100 in this case. So the sum of just this purple part is going to be your A1. And let's try and keep the color coordinate as I've been doing. So we have, in this case, A1, which is 12 over 1,000 divided by 1 minus r. So 1 minus 1 over 100. So that would be 12 over 1,000 divided by 99 over 100. Here we are, divided by fractions again. So I'm going to keep the numerator and I'm going to flip the denominator, 100 on top, 99 on bottom, and then multiply. Well, in this case, 100 is going to cancel out 2 zeros on the bottom. And so I am going to have, just from this purple part, 12 over 990. And that is just the purple part. We still need to take in consideration that 4/10 that's being carried down on it. And so we're going through, we're going to add these together. In order to add these two, I have to have a common denominator, which is why I kept them in tenths and I kept it with the zeros on the bottom for all of them. That's going to make this common denominator easier. Is in this case, I would multiply the top by 99 and the bottom by 99 so I can create that 990 in each of them. So I really have 396 over 990 plus 12 over 990, which is going to give me 408 over 990. And as always, you simplify your fractions for it. And so in this case, we can see that 6 goes into 990 165 times, and 6 goes into 408 68 times. Now, I cheated. I simplified in the first place, but really what you could do is you have 408 divided by 990. We want to check our answer anyway, so hit enter. We have the right answer, and my calculator can simplify the fraction for me, 68 over 165. So that's really what I did for it, and there's no harm in that. I can check my answer before simplification and then use the calculator to simplify it down, because I don't really think it's easy to see that 6 goes into both those numbers. So let's look at number 10. Same idea. So 9 and 10 are stretching us a little bit for it. It's this idea that there is going to be a placeholder on it, and in this case, that's kind of right out above, I have 0.36, then a 1, then a 1, and then a 1, and then a 1, and then a 1, and then a 1. This 36 is not repeating on it. It is going to stay there each time. So this is going to equal, I'm going to keep the 0.36. That is going to be constant. It is not going to change. But the rest is going to. I have to take care of this 1. So I'm going to have a 1 But if I look, there are two numbers to the left of it. So I'm going to have a 0.001. I then have to take care of this one right here. There are three numbers to the left of it. So I'm going to have a 0.0001, 3 zeros to the left of it. Plus, let's take care of the last one. I have this one. I'm going to write a 1 down. However, there are 1, 2, 3. There are four numbers to the left of it. So I'm going to have plus 1, 2, 3, 4 zeros left, then 1, then plus dot, dot, dot. There it is written out for us. Again, I'm going to keep this number as is. It is constant. It's not going to be part of the infinite geometric series. And it's a 36, and there's two numbers there, so that's 36 over 100. Two zeros on the bottom. That is going to stay. That is not part of the infinite geometric series. What I'm going to do next on it is I'm going to list out the other ones. So I have plus. I have a 1. There are three numbers after the decimal, so there's 3 zeros on the bottom. Plus, I have a 1 on top. Boom. There are four numbers to the left of the zero, so I have 4 zeros on the bottom. Plus, I have a 1 on top. There's 5 numbers after the decimal, so I'm going to have 1, 2, 3, 4, 5 zeros on the bottom, plus dot, dot, dot. There is the infinite geometric series written out. And we're only going to focus, again, this is the infinite geometric series on it. This 36 over 100 is going to come down. It stays there. It does not repeat. So my first term, A1, is 1 over 1,000. And my common ratio, well, I'm multiplying by 1 on top. On the bottom, I have 3 zeros. I want 4 zeros. So really, I'm multiplying the bottom by 10. So there's my information. I can go to my formula for this part. My sum is my A1, 1 over 1,000, over 1 minus my ratio, 1 over 10. And so that's going to give me 1 over 1,000 divided by 9 over 10. Dividing by fractions, so we're going to keep the top, keep the numerator, and I'm going to flip and multiply with the denominator. So in this case, a 10 is going to cancel out 1 0 here. And so I have a 1 over 100 times 9, 900. So right here, this purple part, and I'll use purple for it, is 1 over 900. That is the sum of 1 over 1,000 plus 1 over 10,000 plus dot, dot, dot. But remember, I still have this 36 over 100 here that needs to be added to it to get the final answer. And this is why I keep the 36 over 100 and I don't simplify until the very end. It's because the common denominator here is not bad. I have a 100, I have a 900, so I'm going to multiply the top by 9 and the bottom by 9. So I get 324 over 900 plus 1 over 900. And that's going to give me 325 over 900. And rather than just telling you what it is simplified, let's go ahead and use the calculator. I'm going to take 325 divided by 900 so I can check my answer. Please be right. 0.361111. Perfect. Let's hit math, fraction, 13 over 36. So when I simplify this, I get 13 over 36, and there is the repeating decimal answer. Now, I get 9 and 10 are very unique because you have this one number that does not repeat, but the process is the same. Just like on the front page, you are expected to go through the process of being able to identify what is this series as a decimal. What is the series as a fraction? And then what is used to get my answer on it. So this is Infinite Geometric Series. If you have any questions, please reach out.